Welcome back to our study of networks and distributed systems. Based on the textbook by Jim Caros and Keith Ross, Computer Networking: A Top-Down Approach. We're into Module 5 at this point, and we just finished Lesson 3, which ended our discussion of error detection and correction at the link layer. Now we're going to pick up where we left off and proceed to multiple access protocols. We have already noted that there are two types of network links: point-to-point links and broadcast links. A point-to-point link consists of a single sender at one end of the link and a single receiver at the other end of the link. Many link layer protocols have been designed for point-to-point links. The PPP, point-to-point protocol, and high-level data link control, HDLC, are two such protocols that we'll cover later on. The second type of link, a broadcast link, can have multiple sending and receiving nodes all connected to the same single shared broadcast channel. The term broadcast is used here because when any one node transmits a frame, the channel broadcasts the frame and each of the other nodes receives a copy. Ethernet and wireless LANs are examples of broadcast link layer protocols. First, we'll address the issue of how to coordinate the access of multiple sending and receiving nodes to a shared broadcast channel. The multiple access problem. Broadcast channels are often used in LANs, networks that are geographically concentrated in a single building or on a corporate or university campus. Therefore, we'll look at how multiple access channels are used in LANs at the end of this section. Traditional television is one way to broadcast. That is, one fixed node transmitting to many receiving nodes. Nodes on a computer network broadcast channel, though, can send and receive in both directions. The central problem of this arrangement is that of determining who gets to transmit into the channel and when. You and I have learned a number of protocols for sharing our human broadcast channel, such as don't interrupt when someone else is speaking. Wait for an appropriate pause in the discussion to make your point. As children in school, the teacher said, if you would like to speak, raise your hand. Computer networks also have protocols called multiple access protocols by which nodes regulate their transmission into the shared broadcast channel. Here in Figure 5.8, multiple access protocols are needed for a wide variety of network settings, including both wired and wireless access networks and satellite networks. Although technically each node accesses the broadcast channel through its adapter, in this section we'll refer to the node as the sending and receiving device. In practice, hundreds or even thousands of nodes can directly communicate over a broadcast channel. Because all nodes are capable of transmitting frames, more than two nodes can transmit frames at the same time. When this happens, all nodes receive multiple frames at the same time. That is, the transmitted frames collide at all receivers. Typically, when there is a collision, none of the receiving nodes can make any sense of any of the frames that were transmitted. In a sense, the signals of the colliding frames become inextricably tangled together. Therefore, all the frames involved in the collision are lost and the broadcast channel is wasted during the collision interval. Clearly, if many nodes want to transmit frames frequently, many transmissions will result in collisions, and much of the bandwidth of the broadcast channel will be wasted. To ensure that the broadcast channel performs useful work when multiple nodes are active, it is necessary to somehow coordinate the transmissions of the active nodes. This coordination job is the responsibility of the multiple access protocol. We can classify just about any multiple access protocol as belonging to one of three categories: channel partitioning protocols, random access protocols, and taking turn protocols. A multiple access protocol for a broadcast channel with a rate of some number of bits per second should have the following desirable characteristics. When only one node has data to send, that node has a throughput of the channel's full bit rate. When multiple nodes have data to send, each of these nodes has a throughput of the channel's full bit rate divided by the number of nodes transmitting. This does not necessarily imply that each of the nodes always has an instantaneous rate of the channel's bit rate divided by the number of nodes, but rather that should be the average transmission rate over some reasonably defined period of time. Another characteristic: the protocol is decentralized. That is, there is no master node that represents a single point of failure for the network. And finally, the protocol is simple, so that it is inexpensive to implement. Remember from our early discussion that time division multiplexing and frequency division multiplexing are two techniques that can be used to partition a broadcast channel's bandwidth among all nodes sharing that channel. As an example, suppose that a channel supports a certain number of nodes that we'll call N, and that the transmission rate for the channel is a certain number of bits that we'll call R. N is the number of nodes that the channel supports, and R is the transmission rate of the channel. Time division multiplexing divides time into time frames and further divides each time frame into that n number of time slots. Now remember that time division multiplexing time frames should not be confused with the link layer unit of data exchanged between sending and receiving adapters, which is also called a frame. So that I don't cause confusion in this discussion, I'll refer to the link layer unit of data exchanged as a packet instead of a frame. Each time slot is then assigned to one of the collection of nodes. Whenever a node has a packet to send, it transmits the packet's bits during its assigned time slot in the revolving time division multiplexing frame. Typically, time slots are chosen so that a single packet can be transmitted during a time slot. In Figure 5.9 that you see here, we see a simple 4-node time division multiplexing example. A time division regulated configuration allows a node to transmit for a fixed period of time, then allows the other nodes the same amount of time. All nodes have a chance to transmit, and the pattern will repeat. Time division multiplexing is appealing because it eliminates collisions altogether, and it's perfectly fair. Each node gets a dedicated transmission rate of the R divided by N bits per second, the rate of the channel divided by the number of hosts on the channel, during each frame time. However, it has two major drawbacks. First, a node is limited to an average rate of R divided by N bits per second, even when it is the only node with packets to send. A second drawback is that a node must always wait its turn in the transmission sequence, again, even when it's the only node with a frame to send. While time division multiplexing shares the broadcast channel in time, frequency division multiplexing divides the channel's bit rate into different frequencies, each with the bandwidth of the total bandwidth rate divided by the number of hosts. And it assigns each frequency to one of those nodes. While time division multiplexing shares the broadcast channel in time, frequency division multiplexing divides the channel bit rate into different frequencies, each with a bandwidth of the rate divided by the number of hosts, and assigns each frequency to one of those hosts. Frequency division multiplexing therefore creates N smaller channels of R divided by N bits per second out of the single larger full bit rate channel. In other words, frequency division multiplexing takes the total bandwidth of the channel, divides it into frequencies equal to the number of hosts on the channel, and assigns a frequency to each one. Frequency division shares both advantages and drawbacks of time division multiplexing. It avoids collisions and divides the bandwidth fairly among those nodes. However, it also is limited to the bandwidth of R divided by N, even when it's the only node with packets to send. In other words, with both of these approaches, a node never gets to send at the full rate of speed of the channel. The second broad class of multiple access protocols are random access protocols. You need to pay special attention to this class of protocols because it is the protocol used by Ethernet, the most common local area network protocol in use today. In a random access protocol, a transmitting node always transmits at the full rate of the channel. When there is a collision, each node involved in the collision repeatedly retransmits its frame or packet until its frame gets through without a collision. But when a node experiences a collision, it doesn't necessarily retransmit the frame right away. Instead, it waits a random delay before retransmitting the frame. Each node involved in the collision chooses independent random delays. Because the random delays are independently chosen, it is possible that one of the nodes will pick a delay that is sufficiently less than the delays of the other colliding nodes and will therefore be able to sneak its frame into the channel without a collision. We're about to discuss some of the most commonly used random access protocols, the Aloha protocols and the carrier sense multiple access protocols. Ethernet is a popular and widely deployed carrier sensing multiple access protocol. But before we start that, let's take a break now and update our study guides and review our notes before we start this section.